Okay. As for now, we have 4 presenters already showing up. I'm not sure the fourth one, but he might be coming. But I think we're gonna go with our original plan. Each presenter has 12 minutes in the presentation, followed by 3 minutes of question and answers. Without further ado, I'd like to invite the first presenter.
Yes, the first presenter for the topic of study the ground settlement of soft clay using discrete element method, Mr. Phairot Khajorn Sakun.
Thank you, please.
Good morning, everyone. My name is Phairot Khajorn Sakun. I'm a master student from Ksesat University. Today, I will present about the study the ground settlement of soft clay using this discrete element method. I have an advisor is Professor Dr. Sutisak Soralam, and a co-advisor is Assistant Professor Dr. Suriyon Pempamod. The presentation will cover 5 topics, main outline that show in the PowerPoint. Start with the introductions, and following with the problem statement that we found in in the Thailand load. After that, we are moving to the modeling on the soil layers in Thailand, where the discrete element method. Later that, we will show the results of the simulations and closing with the conclusion of the study that explain what we found from the modelings. First, due to the limitation in the cities like Bangkok, they have a lot of facility on ground, so it's quite difficult for expand the underground. It's quite difficult to expand the other facility like underground electrical system or pipelines. So the underground electricity is the underground works or tailorless technology might answer this way to solve the solution to solve this problem due to the limitation of the city areas. So in Bangkok, most electricity are buried under the ground, especially in the main cities, as shown in the slide. As you see, they have a lot of systems buried under the ground. And the most commonly method that we use to bury the electrical systems in Thailand is horizontal directional drilling or HDDs. The HDD is effective way that they have several advantages. Like cost effective, the SED construction cost is more cheaper than the other method like open and cut and pipejackings. Following the quick installation, due to the limitation of the loads, we have to recalling the load as soon as possible. So if we use the other conventional way like open and cut, they might take a weeks to preparing works. But if we replace with the HDDs, the construction work can be reduced significantly. Later as the flexibility and durability. Following with the environment failures, the HDD itself is not quite effective to the environment aspect as similar with the other methods like open cast. Open cast you have to reclaiming lands, and you have to put the clay to put into the other place that might take a environment hazards. The method for the HDD is very simple. The component of the HDD machine is covering with the directional machine itself and the rotating pipe specialized. The installation is starting with they have a pilot or a pilot deal bit that will deal to add the guideline from the start entry to the exit entry that the pipe will be exit out. Later that, there will installation the head that will deal out the diameter that what you design. At the final state, that will pull the bilateral HDPE from the exit to the entries. So, in Thailand, we have faced a lot of problems that due to the settlement, leading to several problems like traffic congestion and serious injury, as well as the consequent damage and damage of the underground facility. Like, as I show in the picture, that they have a settlement of the road that will cause serious injury and might lead to the traffic congestion as well. This slide also shows the behavior of the settlement of the ground in Thailand that will construct the electrical system under the ground by HDD method. This is the consequence that we found. So now we're moving on to the modelings. The modeling is based on the discrete element method that consider at 3Ds via the PFC 3D programs. The discrete element method may be consist of two majority theories between the Newton's second laws and the force displacement laws. As the relationship between Newton's law and force as shown in the two equations in the slides. In the PFC 3D or discrete element method, they consider the soil particle as they consider clay or soil as a particle which have a relative contact each other. As shown in the slide, in the picture in the left-hand side, each particle have a relative force to attack each other. As you know, there's clay, they have a contact force to link it out between its particles. In PFC, also consider at this as well. The simulation is starting with the equation of the motions, and they consider force between its particles and the displacement during the force effect on its particles. Later that, they will use the time step. Time step is like a time that accelerates time that the particle, once the particle apply the force, what the behavior was during the time that increased, that the behavior of the particle that show, that will record it where the time step that we adjust. So the PFC 3D in the program is like as shown. We consider the clay at the particle. In PFC, they call it ball particles. The result that we try to simulate that we try to find out the settlements, the gas settlement that occur or SMAX. After the equation works of the HDDs, the equation work can be determined by in the PFDD. They also have the function that's called the maximum unbalanced force. This maximum unbalanced force will detect the chaining of the force by the simulation varying depth of the HDDs works. We can plot it out, the settlements, and after the equation work as shown in the graph, we notice that during the 5 meter depth from the ground levels, the settlement will occur significantly, while the other settlements, while the other depth will decrease as shown. Once referred to the consequent damage due to settlements based on the criteria that the Department of Rural Roads from Thailand they classify. They classify in 4 levels. The first, the level 0 is no cracks or no settlement. That's classified as degree of damage is no damage any occurs. Following with the level 1, crack, less than 1 centimeters or settlement less than 3 centimeters. This one classified as a minor damage. Level 2 is a crack less than 5 centimeters or settlement less than 10 centimeters that classified as intermediate damage. Following with the level 3, cracks more than 5 or settlement is bigger than 10 centimeters, that is significant. From the criteria that we classify at one depth, we measure one depth. We measure that if the settlement is occur more than 1 centimeter, we will record for the inference. That's what we can plot out the inference zone on each depth of the HDD work. It's noticed that at the deepest, like 1 meter, the inference zone might be expand much higher than the other depth. The state contour at the total state also plot in the exact plane to see the state around the HDD work. It's noticed that around the HDD work, they have a lot of state that occur in the soil particles. So that's all for the presentations.
Thank you. Any questions from the audience? Can you briefly describe how you calibrate your model? For example, the contact stiffness and also the bonding, because you didn't mention that in your slides.
Most the parameters like contact force or the stiffness of each particle that come from the that come from the calibration process of the direct shear test.
Direct shear test on clay.
Yeah. Direct shear test on clay.
Okay.
Once we perform at the lab, we also modeling compare with the program also.
I see. Thank you. Any other questions?
I have some question about why you select DM for soft clay, because normally for DM we will use for the sand particle, something like this.
This one we consider that regarding to the K property itself, normally there are saturation with the waters, so they have อาจารย์ครับจะรบกวนอาจารย์ช่วยแปลแล้วกันผมอธิบายไม่ถูกก็คืออย่างของผมตัวเนี้ยผมจะมองว่าเคเนี่ยมันปกติเนี่ยตัวพื้นตัวด้วย property ของเคเนี่ยมันจะเป็นเหมือนสภาวะด้วยอิ่มตัวด้วยน้ำครับเคที่ผมคิดในการโมเดลก็มองว่าตัวเคเนี่ยมันมีแรงดึงดูดระหว่างตัวเม็ดดินซึ่งมันก็ไม่ได้มันอาจจะต่างจากแซนนิดนึงครับแซนมันไม่มีตัว C cohesion แต่ว่าตัว K เนี่ยมันมีแรงดึงดูดซึ่งผมโมเดลในแง่ของในรูปของการเกิดพวกfriction ระหว่างเม็ดดินนะครับ
Okay, he said he asked me to translate in English, or do you want him to?
I just want to make a comment.
Okay.
Clay can be simulated in the discrete element model because natural clays exist as flocculated clay. They are not clayey anymore. Therefore, in the same way that you model sand particles, flocculated clay particles can be modeled with DEM with the contact forces that he actually put in his second slide. So it is possible to simulate clay behavior with DEM.
Thank you, Professor.
Any common questions? If not, let's give a round of applause for the presenter. Thank you. Our second one will be given by Ms. Asmi. The title of the presentation will be the numerical and numerical sediment analysis comparison for the horizontal directional drilling works.
Okay, thank you, Chairman, for the introduction. I'm Atika Azmi from Oracle, Malaysia. Today my presentation title is Empirical and Numerical Settlement Analysis Comparison for Horizontal Directional Drilling HDD work. This is some introduction for the HDD work. HDD work is a method of installing underground pipelines, cable and service through a trenchless method. It involves drilling along the proposed alignment. Normally we do HDD where the open cut is not possible due to the site limitation or also not permitted by the authority. So HDD would normally raise a concern on the potential ground loss issue which can result in the ground settlement, and the calculation of the settlement involve estimating the volume of soil that will be displaced during the drilling process and determine how much settlement will occur as the result. In this paper, we will discuss the settlement analysis from both empirical and numerical analysis used to compare against the monitoring data. Okay, this is a brief introduction to the project background. So actually the site is located at the Klang Valley, Malaysia, and actually the HDD work is drilling to the existing expressway. And the ground level at this area is ranging from the reduced level 24 to 24.8, which generally the topography is considered flat. Okay, so this is the project detail on the proposed HDD work. For this project, we are using 8 numbers of 110 mm HDPE pipe. So the drilling length is about 85 meter. And the maximum reaming size is about 500. The depth is ranging about 5 to 5.5 mm, 5 meter. And the number of pit is, we have 2, which is entry and exit. Okay, for this project, actually we have carried out 2 borehole for this area. And based on the data collected, we plotted the SPTN versus depth, which you can see on the graph. For the first 10 meter, it consists of silty sand with an average of SPTN 6. And then the second layer is still with the same material and with SPTN ranging about 11. And at 15 meter depth, hard layer is found. Okay, so based on the data collected from the borehole and also from the lab test, the soil can be classified as medium stiff silty sand. So normally for the silty sand, the void ratio typically range from 0.4 to 1 meter. For this paper, we are adopting 0.5 in the analysis. For this project, we are unable to carry out the CIU test due to unable to retrieve the undistorted sample. Therefore, the value for the friction angle and also cohesion value, we are assuming from the engineering judgment and also past experience in the similar ground condition. So it goes the same for the young modulars. We are not having any pressure meter test carried out. Therefore, we are using the SPTN correlation to estimate the value of E. For the groundwater level, the data recorded from the borehole show that the groundwater level ranging from 3 to 5 meter below the ground. So we are taking 3 meter as our conservative approach in the analysis. So for the empirical approach, we are using the Gaussian distribution curve, and the formula is as shown in the blue box is the maximum settlement S max equal to V d square over 3.192 I, which is V is volume loss, D is a tunnel external diameter, I is a horizontal distance from the tunnel center to point of inflection, where K is a soil constant, Z is a depth of tunnel axis. Okay, so for this project, this is the typical soil constant that we can use. Since the HDD work drilling through the medium dense silty sand, so for this analysis we are adopting 0.5. So before we go to the calculation, there are several assumptions made to estimate the ground settlement, which is the first one is a drilling depth. For this project, the drilling depth is about 5 to 5.5 meter. Since shallow drilling have a higher chance of the surface collapse, we are using 5 meter as our critical depth. So for the size, the reaming shall be carried out in sequence. This is to prevent the tunnel from collapsing due to the sudden enlargement of the pipe. So the volume loss is actually the difference between the reaming size and the pipe volume. So the illustration actually show the possible type of arrangement for the 8 number of the HDPE pipe. So based on this illustration, the volume loss is ranging about 50%. So we are using 50% as our volume loss. So based on the assumption and also the formula, the calculated ground settlement using this Gaussian curve is 15.65 mm. So we go to the numerical method. So this paper discussed the numerical method using plexis to calculate the ground settlement. So for this model, we are using 2D plexis and we are model using more column. For the soil drainage type, we are using drain for the silty sand and also undrained for the bentonite property. So the mesh size that we are using is a medium size mesh, and we are using tunnel feature to generate the opening. So for this project, we are having two construction stage, which is the first one, initial stage. The second one is drilling using 500 mm diameter. So this is the plexis input and also geometry. For the soil layering, we are using medium silty sand and also stiff silty sand. For the bentonite property, we are applying it at the opening, as the bentonite we are using for the stabilizer to prevent the soil collapse. So based on the input and also the geometry, we run the plexis, and from the analysis, the estimated ground settlement using plexis software is 15.31 mm. So the verification verification of empirical and numerical analysis, again monitoring data. For the monitoring data, we are using settlement marker to monitor the behavior of the settlement, but also settlement marker is act as a precautionary and also warning system to inform any instability during the HDD work or after the HDD work. So the settlement actually we install at the emergency lane and also the fast lane of the highway. So based on the table, this is the recorded data during the HDD work. So the maximum data of 16 mm is recorded when the reaming size is at the maximum 20 inch, which is about 500 mm. So actually the asterisk is referring to the no reading recorded due to site constraint. Okay, so site inspection for validation purpose. So this site inspection we carry out to ensure the reliability and also the accuracy of the data. So the first one is depth. The depth we need to check is because any changes in depth or any changes in size will affect the settlement calculation. So you need to check the depth during the piloting whether it's same with the proposed design. So the second one is the pipe arrangement. The number and the arrangement of pipe must be checked to confirm the assumption of the volume loss. So based on the data we collected from the empirical and numerical method and also the data recorded from the settlement marker, so we tabulate and the summary is shown in the table. So using the Gaussian method, the difference in percentage against the monitoring data is about 2.13%, which for plexis software is about 4.31%, which we can conclude that the difference using various range is about 2 to 4%. So in conclusion, a comparison of ground settlement between numerical and empirical approach has been carried out. Both numerical and empirical can be used to estimate the ground settlement with accuracy ranging about 95%. From this analysis, we show that the ground settlement by empirical method can be used as a conservative to estimate the settlement, the surface settlement. So with that, I would like to thank you for your attention.
Thank you. Any questions and comments? Yes, please. Yes.
Thank you. Very good. I just wanted to ask you, was the analysis carried out before the work was done or afterwards?
Okay. Actually, the analysis was carried out before the work done because we need to estimate the settlement.
No, sorry. Would you please just tell me, was the analysis done first or the work done first?
The analysis were done first.
Thank you.
Okay.
Any questions from the audience? I look at your domain and mesh, found out that the excavation is much smaller compared in your domain. Is there any particular reason? Because you have very large domain and then the excavation is very small.
Oh, okay. So actually, that one should be no problem because the distance need is about okay. There's no difference in that way lah.
Right. I was thinking perhaps you can use a smaller.
Yeah. Maybe I take note on that. Maybe the next analysis we will use that too.
Okay, thank you.
Okay.
Any comments? If not, thank you, Ms. Asmi.
Oh, okay.
Thank you.
Okay. For the next, the paper ID 4008 computer vision for particle size analysis of cross-grain soil, Professor Sompot Yuwai.
Okay, thank you for the chairman and co-chairman to introduce me. So actually, this one I have done this research according to COVID, because in that time my student cannot go to the lab and do the SEAP analysis. So in that one I try to make some tool that how to get the grain size distribution that student can work at home. So actually for the inspiration, they have the paper published in 2017 in Acta Geotechnica. They use the DSLR camera to take the photo of the particle of sand sample, and they feed the sand sample by using some belt conveyor. So I in my idea I said, so this one requires very sophisticated laboratory and cannot do at home or cannot do at the site. Can we make it easy? Because right now we stay in the AI age. We have a lot of library. So we can write really easy Python code. So if we have the SEAP analysis like that, this one I obtained the sample of about 50 specimen of sand sample. How can we capture the particle size according to this one? Instead of not have done SEAP analysis. So right now nowadays we have a lot of library. This one I use a library is so-called OpenCV. OpenCV is the so-called open source library. They made in C++ and it can also run in Python also. I used two of the library is so-called adaptive threshold, and the other one is called file contour. The adaptive threshold is that I would like to, for this one, if I would like to detect the hand, the edge of the hand, so I try to remove the church, remove the face mask, and the file contour is that to let the computer to find the boundary as the contour. So if we can use this kind of tool library and open source, you can modify insights, and we can I have hypothesis that is it possible if I use the OpenCV and try to capture the soil particle. And this one, if I draw some of the rectangular, I can find the size of the soils. And the problem is that when I use the computer to find some of the dimension of the soil in the picture, the result is in pixel. I can tell, okay, this soil have the length of the width of the soil particle about maybe 10 pixels or 100 pixels. So I have to change the pixel into the actual length. So how can I choose this one? So I use the, I don't know, I can open up. Okay, I use the, it's so-called AIUCO. It's the one kind of the target. This one is really fast. So this one is my student. I can use the computer real-time detection, the target in this one. It can detect where is the target it is, what is the size of the target. It's really fast. You can see here, he moved, he have about he has about 4 of the target, and we detect it simultaneously together. And also the concept of that one, if I have this kind of AUCO target, we can determine the size of the target, and we also get this one called the T-vector to determine this target. And also in this target, I also extend this application to the pilot test as well. But I will not talking about today. Just install the target on the pilot test and record the deformation. And after that, I compare with the pandemic pilot test, and result is quite okay. I will publish this soon. And it's not only this one. This one, the people will use to control the robot. They can know the location of the robot and can run in the field. So we come back to our case. So how can we determine the size of the soil in the real world? We use the AR or augmented reality. So I setting the target size is about 20 millimeters. So that means per meter is about 80 millimeters. And after that, I use this one is so-called pixel to length ratio. So it's the length of the length LP is the length of the pixel. We record in library, divide by the actual length. The actual length is about 80 millimeters. And after that, I can, if I use this kind of technique, I can obtain what is the actual size of my soil. So this one is really easy. You just print out A4 paper. Just spread your sand on your A4. Use mobile phone, take the photo. And the library will record the target and find the size of the target. And after that, you can find the size of the soil sample. The workflow is like that. Firstly, you're starting with convert picture to the gray sample, reduce noise, use adaptive threshold as I mentioned before, find the contour, calculate the particle size. After that, I calculate for the gradation curve. So this one is one example that is a soil we can connect. So the result is like that. This one, I mask the target because I don't want computer to detect at the target. And after that, I just detect this one is one of soil. And actually, they have some hyperparameter. Also, we have to calibrate because we use the library. We have to calibrate. They have the block size and see. We're not talking the detail. I use the optimization. It's so-called particle swarm optimization to find the best optimized parameter that can detect the soil. So this one is the final. This one I use actually is the cooperative research. I cooperative with the soil testing company. They have some of the people send the soil to test the company. I let him to take the photo. It's a co-author of my paper and just find it. So for the cost grain, the result is quite well. MAPE is the mean absolute percentage error is we can reduce up to about 6%. But the file content, the file particle is not quite good. So in the future, maybe I will extend this research, maybe just do something, maybe break the soil into smaller part, or maybe use the high performance computer. But because this one I used only the iPhone 8. The solution is not good. If I change this one to be maybe DSLR or high performance camera, maybe we can detect more file parameter. And also actually in the class, I also developed the web app also, and let the student who use it just upload the JPG like that. And after that, upload into the server and run this program. And after that, just when I upload it and wait for a while, let the computer calculate it, they will get some, okay, just wait for a while because it's a free server. actually, I captured this one. Okay, and after that, and you can see it here. And after that, they have the gradation come out. So that means if you work in the field, you work in the borrow pit, you can obtain the gradation immediately. Even if we have some error, but it's better than you send to the lab and test it again. And this one is, if you see it, it's not only the gradation. I also perform soil classification altogether. You can see that the soil is SW, SP, or dual symbol, and so on. You can see what kind of soil we get to in the field. So the conclusion is that this study proposed the computer vision and combine the tracking the picture with AAUCO to estimate the soil particle, and also the error of this one mean absolute percentage error for the fine grain soil is about 6%, but the coarse grain soil about 6%, and for fine grain soil I think it's still quite high. Have to development. I mean, maybe in the future you have to use the maybe high performance camera, or maybe have to hybrid with some of the deep learning visual transformation or CNN to hybrid with this one. Maybe it's become better. One detect from computer, and this one detect from deep learning and combine it. Maybe for the fine grain, maybe it can be find some parameter to adjust. Maybe it come better. And so that's all for my presentation. That I would like to share. Actually, the COVID is good. I can stay at home and coding, and I can make it and to solve the pain point. And I use this one for teach soil mechanics labs for 2 years. Students can use the soil at home, maybe soil at the grass, maybe the sand around the home, and just can send me the report. What is the gradation of the soil? What is the without do any kind of SEAP analysis? Thank you very much for attending my presentation.
Any comment and questions? Let me ask you one. What's the resolution of the method that you proposed? I mean, the smallest, the length with a good accuracy.
Accuracy right now is about 5 millimeter.
5 millimeters.
If lower than this, right now the result is not quite good because the problem is come from it's not only the resolution of the camera, it have the noise of the camera as well. Maybe computer is not detect the soil grain, detect the noise from the camera. For in the future, maybe we try to change the camera, maybe the better one. Because actually for the iPhone, it's not good for take the photo because they process it before. It's not the raw.
Right.
You make a lot of
And
noise.
then I noticed that you compare with your sieve analysis. But when we do the sieve analysis, you see the sieve with all the opening that is not really measuring the shape and size of the particles. So what's your comment on that? Because you mentioned about the error, about...
Okay. So actually I have done several ways. Maybe find the real area, maybe, but I select this one I used for the rectangular. Rectangular just means I width and length of the particle and find the average. And this one I found is quite closer to the SEAP analysis. Right. If use the real parameter, I think it's produce the more error compared to this one.
Right, thank you. Any other from the audience?
I have some small question, Professor, because I would like to know how to set the amount of the sample that you will use for this method. For example, in the SEAP analysis, for example, like 1 kg for the SEAP analysis, and this one how to select the volume or the mass of the soil for this kind of method.
So actually I have to tell you honestly, now it's not yet set. Because I have to say this one is starting a research. Maybe in later on, maybe we have find some of the maybe standard to prepare it. So this one actually they have some error because I just tell maybe the worker in the lab just press this one on by the hand. But actually it's not good. Should press on maybe some kind of the mesh or sieve or several kind of layer the sieve to get this one. But in my attention, I would like to make it maybe easier as I can. And I hope that this one could be used in the field. Maybe we just have an iPhone and one piece of paper, you can get the gradation. It's like that. But in the future soon, I will publish in journal, and I will set up some of the sophisticated method and compare to. But right now, it's in the progress of research.
Thank you. Okay, so thank you, Professor
Okay, thank you very much.
Sompot. Thank you. Okay, for the last presentation for this session is the paper ID 8080, the response of the railway bridge and support region to moving load, a brief numerical study by Mr. Arita Baji. Please, okay.
Hello. Very thank you all of you to give me an opportunity to present my piece of work in this valuable event. So my topic is basically a small numerical analysis based on the railway bridge project. So this is my sections which includes introduction, some literature review, some overview of the project, and the method of the numerical analysis that we have, that I have engraved, and some results and discussion at the last section. So the main major geotechnical research that needs to take concern about, that is the end of the bridge end zone. What we generally overlooked, because there is a huge amount of geotechnical involvement there at the end of the bridge zone. So due to the change in the vertical stiffness, you can say, there is a uneven settlement take place at the end of the bridge zone, which has been reported by several researchers like Peduto, Q1, and they have reported that due to this reason, there is a huge amount of vibration that can take place at the end region, which may cause the discomfort to the passengers. So we have to go through thoroughly about the influence of the geomaterials, which is affecting the substructure behavior. So we can see this through picture. This all are transition zone. Some transition zone at the right corner, it may this can be a presence of the embankment, and the lower one, you can say is a type of filling which is supported by a substructures. So essentially, it's a retaining wall which is supported by backfill. That can be equivalent to that problem. So there's some literature review that I have gone through, where they have done some extensive numerical work, both in 2D and 3D. And also they have found some essential elements which determines the track behavior also. So based on that, the objective mainly adapted is to build a finite element model using a open source software, which is OpenSys. And also how we taken the load only based on the static approach, and also some investigation done on the some critical component of the rail track. So here is the overview of the rail bridge, where basically this the left one is the project we are dealing with. Uh, um, so all the Indian codes that has been employed here is basically a railway track which essentially built to support axle load up to 25 ton. And you can see in the picture there is a type of soil also given, which is basically the layers of the soil and the type of the soil which was found by boring, and this has been provided by the railway authority. So this is my specification of the FEM model, which you can see that there is an abutment there, and which is supported by the pile cap and a pile. So these dimensions mainly chosen by a calibration process, by giving a load and just observe the change in the response. The length of the domain has been chosen at that point where there is a negligible change in the response. Also the mesh has been chosen, the denser mesh has been chosen. You can see that behind the wall, and also there are some other criteria also based on the spacing of the sleepers, the vertical stress convergence at certain point at lower depth and higher depth, and also due to the thickness of the soil, this mesh has been prepared. So here's a part of the part A. We actually model the soil as a quadrilateral, 4-node quadrilateral element. And basically the preliminary analysis shows that beyond 20 meters there is very less effect on the track region. So we just represent the results for up to 60 meters also to take care of the larger transition region. So as we are dealing with the 2D modeling, so we have to go through some assumption. You can see that in our case, there is the existence of the side walls which prevent the out-of-plane deformation. So there is one of the great assumption which reduce it from 3D to 2D. Also the out-of-plane resistance by the pile we considered, which essentially leads us to 2D modeling of the substructures. And also the railway outward vibration is, in this case, is neglected due to the assumption of the very rigid fasteners which essentially hold the rail to the sleepers. So coming to the structural model, some elastic beam element has been used to model the structures, as we are not concerning with the structural deformation explicitly. We just that's why elastic beam column with very high stiffness we have considered here, and also there is a we are not considering the relative movement of the wall and pile cap. So we model it as a monolithically. That means all the structural sections are discretized in an element without employing any type of interface elements or connecting elements. So these are the two models of interface element that we considered. We have been used the node-to-node contact element, which especially works on the KNKT concept, that is normal stiffness and strip stiffness. Where normal stiffness has used to control the penetration of the structure into the soil material, and stick is the sliding between, and also KT controls the slide of the structure along the soil. So we are limiting the as we don't want in any numerical error which has been generated due to the analysis, due to contact. So we change the KNKT parameter, normal stiffness, to control the node-to-node contact element to work properly. So here the rail we have considered here is also elastic beam column element with very high stiffness, and this is the rail cross section. Basically, actually it is bull-headed, but we simplified it to into rectangular headed to just to easy for our calculation. And another essential parameter is the rail pads, which essentially connects the rail to the sleeper. So we go for the Kelvin-Voigt model, which essentially consider the viscous dashpot that is parallel with the with the spring, which also has been adopted by the several researchers before. So here is the sleeper element. We also actually a sleeper is cross section is like that. We just for our convenience we make it into the triangular cross section, but maintaining the bending stiffness constant. So this is a total arrangement of the rail pad and sleeper. So the coming to the constitutive model of the geometries, as we have seen from the data that all maximum belongs to the silty sand. So we can assume that this type of granular soil property depends on the pressure at the current confinement. So the pressure dependent basically means that the stiffness will change according to the current confinement. The backbone curve is denoted at a certain pressure, and all the nature of the behavior will controlled by the this equation that has been given below the picture. So coming to the validity check, we have chosen a earlier research Sugubara, and we have found that it is quite very good match with the previous model. So this is a moving load that we have obtained. This is a standard axial load. We have chosen the maximum axial load around 20.5 ton, and this is the moving load diagram. So some result discussion is, we can see that we have chosen the two value of the rail pad, very low rail pad value, stiffness value, and high stiffness value, which is based on the paper we considered by Hassan et al. And we can see that for the lower stiffness value, there is a transfer of higher transfer of load to the rail, which essentially controls the deflection of a rail and also the deflection of a sleeper. So also the lower stiffness ratio between the rail pad and the sleeper, which limits the transmission of the additional stress to the sleeper below, which also a considerable factor that we need to take care of. So this is the stress contour that we can see here. We can see that for the lower stiffness value, there is a transfer of load is circulating from that lower depth to the very higher depth. So for low rail pad, we can conclude that the more deeper region is being affected by due to the lower stiffness region. So coming to the lateral displacement of the abutment, we can see that due to the is actually the converse. When we using some higher stiffness value, the lateral deflection of wall is more compared to the lower K-pad stiffness. So that can be explained by the horizontal stress contour that we can see from the. So from that we can find some conclusion that the reduction in the overall track stiffness and the transfer of maximum load is very much dependent on the rail pad stiffness that we need to take care of, and also the stress contour that we have for more elaborating the situation, we need to take care about the stress amount that has been circulating through the geomaterial, and also the bending moment and stress shear force diagram also depends upon the horizontal stress diagram behind the wall, which is very much dependent upon the rail pad value. So this future work can be extended to the number of locos. We can increase the number of runs and take care of the long-term behavior of the situation. So reference, thank you for
Thank you. Any common questions? Yes, please.
That was very interesting. You obviously put together a very complex finite element model, but has any of this been tested by actual measurements?
You're asking me about any field test, right? Any field test. You are asking me for some validation in the field. Right?
So comparisons have been made with actual movements in the field?
Actually the project is in the middle. Basically, this is one type of approach that we verified with the previous research. We have to take...
but in India... In India...
We just take care of the previous research which has been done. But till now, the project is going on, so we hope that this model will work in the future good for our case, but we don't sure that it will work with the field measurement, that only.
Yeah, my own experience, although now well out of date, is that with such a complex model, you can always get the correct predictions after you make the measurements.
Okay. Yeah.
Right? I believe that predictions are only really worthwhile if they are made before the field measurements are obtained. Otherwise, as I say, with so many variables in your model, you could change those variables to always get the correct predictions.
Okay.
Thank you.
Okay, thank you for the valuable information.
Anyone from the audience? You mentioned that in the future, your model gonna account for the material degradation due to model the degradation process. And then for the open seas, probably you need to have a user-defined material model implemented into the program. It's not
simplify your question.
How are you gonna use the open seas to model the degradation of your the subgrade material due to the traffic load? It's a moving load.
The direction test, and we know the response of the direction and triaxial. So before applying this model, I have just a small dummy model has been created using this element, pressure dependent element, and is it
doing the cyclic effect in your model? Thank you.
Ki-Hok Inc. And the second is Yongping Jason O. And the third is Omer Altaf. The fourth is Mahabab Sadiq. The fifth is Chia Jan Sai. The sixth is Seyong He. The seventh is Anissa Tadiana. The eighth is Ariska Radim Ani. I'm sorry if I spell your name is in the wrong one. So please get the receipt at the payment counter. Thank you.
Thank you very much. Thank you. We'll see you around 10:45 for the second session of a numerical analysis. Thank you.
2003. Despite the available of the theory, the apparatus, and the measurement method in the literature, to the author's knowledge, these have not been fully explored and utilized in Indonesia. The theory has not been disseminated well, and the apparatus has not been built and used. Therefore, it is considered urgent to introduce the development of volume change constitutive surfaces for soils in Indonesia. For the materials and method used in this study, the materials is originated from mud rock from Cisemang region, West Java province, Indonesia. The mud rock was crushed and then compacted using modified Proctor method. A standard test for saturated consolidation test was performed until a maximum effective stress of 1000 kPa. The void ratio versus effective stress curve were then obtained. The soil water characteristic curve, SWCC, was obtained from the prediction method of Perella et al. 2005 and was used in the development of water content constitutive surface. In the plotting of SWCC, the recommendation of SWCC plotting in Fredlund et al. 2001 was followed. The curves of void ratio versus effective stress, void ratio versus matrix suction, water content versus effective stress, and water content versus matrix suction serve as the 4 planes in volume change constitutive surfaces. Using these planes, the volume change constitutive surfaces were computed using the assumption in Fredlund and Raharjo 1993. The assumptions are the values of AT and AM coefficient are constant for the same value of void ratio. Also, the values of BT and BM coefficient are constant for the same value of water content. Index properties of the crushed mud rock is shown in the slide. It has liquid limit of 64.6, plastic limit of 31.5, and plasticity index of 33.1. It was then compacted at a water content of 16.1% and achieved a dry unit weight of 17.9 kilonewton per cubic meter. The results of consolidation is plotted in arithmetic scale as shown in figure 2A and is plotted in a semi-logarithmic scale as shown in figure 2B. The basic relationship in soil mechanics was then used, that is degree of saturation times void ratio equal to water content times specific gravity. Since in the consolidation test the soil is saturated, the degree of saturation is equal to 1. Thus, the gravimetric water content can be calculated using the relationship of water content equal to void ratio divided by specific gravity. The results are shown in figures 2C and 2D. Figure 2C is the curve of gravimetric water content versus effective stress in arithmetic plot, whereas figure 2D is the curve of gravimetric water content versus effective stress in semi-logarithmic plot. The curve of gravimetric water content versus effective stress in figure 4A and 4B were then converted to the curve of void ratio versus effective stress. The void ratio is calculated using the gravimetric water content and the shrinkage curve. The shrinkage curve is a relationship between the void ratio and the product of gravimetric water content and the specific gravity. In this study, the shrinkage curve is obtained using the prediction method of Fredlund et al. 2002 using the index properties as input. The predicted shrinkage curve for compacted mud rock is shown in figure 5, and the void ratio versus effective stress is shown in figures 6A and 6B. Figure 6A is the plot of void ratio versus effective stress in arithmetic scale, whereas figure 6B is the plot of void ratio versus effective stress in semi-logarithmic scale. The volume change constituted surfaces were then developed using the assumption in Fredlund and Raharjo 1993. The volume change constitutive surfaces are shown in figure 7A to 7D. Figure 7A and 7B are the void ratio and water content constitutive surfaces in arithmetic plot. Figures 7C and 7D are the void ratio and water content constitutive surfaces in semi-logarithmic plot. In this volume change constitutive surfaces, the parameters of unsaturated constitutive surfaces that are AT, AM, BT, BM, CT, CM, DT, and DM can be identified. These parameters can be used in the calculation of volume change of unsaturated soils. The volume change constitutive surfaces in between the zero net normal stress and the zero matrix suction planes can be obtained from a laboratory measurement using the Kenneth unsaturated consolidation apparatus. The Kenneth unsaturated consolidation apparatus was proposed and explained in Raharjo 1990, Raharjo and Fredlund 1995, Raharjo and Fredlund 1996, and Raharjo and Fredlund 2003. Based on this design, a Kenneth consolidation apparatus is being developed in Soil Mechanics Laboratory, Faculty of Civil and Environmental Engineering, Bandung Institute of Technology, ITB. The apparatus at its initial stages is shown in figure 8. When this apparatus has reached its final development, a measurement of volume change constitutive surfaces can be performed in addition to the. In conclusions, number 1, volume change constitutive surfaces for compacted crust mud rock were developed in the preliminary stage. The constitutive surfaces were developed utilizing the result from a standard saturated consolidation test, predicted SEAGC-AGSSEA, predicted shrinkage curve, and a prediction method for volume change constitutive surfaces. Number 2, volume change constitutive surfaces. In the volume change constitutive surfaces, the parameters of unsaturated volume constitutive surfaces that are AT, AM, BT, BM, CT, CM, DT, and DM can be identified. These parameters can be used in the calculation of volume change of unsaturated soils. Number 3, based on the design in the related reference, a Carnot volume change apparatus is currently at initial stage of development in Soil Mechanics Laboratory, Faculty of Civil and Environmental Engineering, ITB. When this apparatus has reached its final development, a measurement of volume change constitutive surfaces can be performed. And these are some references that are used in the study. Also this one, and references by Krishnanto et al. 2002, the one with the DOI link, summarize the development of the unsaturated soil mechanics in engineering practice in Indonesia. By this, I end my presentation. Thank you.
Thank you. Any questions, comments? In terms of getting the 7 parameters that you were saying, you have some technique, and can you briefly describe how you do the calibration? By simply the curve fitting or any kind of thing by making the equation linearized or some other methods?
This one we only have the plane, the in between plane, the one that measure one is this one, and then the in between plane is the 3-dimensional part is obtained by a prediction. That is why in the future we would like to verify that prediction 3D surfaces using this apparatus.
So for these tests, for one of the K-non unsaturated consolidation tests, how long you will take to perform one test?
This one we have not performed this test.
Right, but from the literature that you have seen,
it is roughly around the time that test to obtain the SEAGC-AGSSEA using the pressure plate.
Okay, right.
But actually we have not we are developed this the apparatus, and the apparatus is not available in my lab.
Right. Thank you. Any other?
Can I ask some question about the basic equation for the unsaturated soil, which model that you use to predict, like together with this parameter, the name of the model, like that?
Yeah, actually, my apology that the equation is not available in the presentation, but it is available in the paper. Volume change, we have the equation of we have the volume change is mainly on the void ratio. That is the result of the consolidation test, which is the, can I show here? Which is this plane. This plane is actually the result of consolidation test. This plane is in arithmetic scale, and also this plane in semi-logarithmic plane. But for unsaturated soil, the volume change comes not only for void ratio, but also for water content. That's why we need 2 equations, which is written in the paper.
Because normally for the unsaturated equation or model, normally they have around 10 or 12 parameters already. So this one is the additional or the parameter in that equation?
Yes, yes.
The parameter in that equation?
Yeah.
Oh, okay. Thank you.
Okay, if there's no more questions, thank you, Professor Cucinato. Thank you.
So far, the next presenter is Dr. Omar Dr. Omar Altaf in the topic of effective stress analysis of the gravel-dominated soil in the lower Wyalo Plains, New Zealand.
Hello, everyone. As she has already announced, my name is Omar Altaf, and I am here from University of Auckland, New Zealand, and I'm also associated with Otago Polytech as a faculty member. This research which I'm going to present today is part of my overall PhD thesis which I completed this year, and this is just one of the last bits in which I have performed the numerical analysis. So I will talk about effective stress analysis of gravel-dominated soils in the lower Wairua Plain of New Zealand. So most of you are already familiar that liquefaction happens when granular loose saturated soils are owing to the dynamic load like earthquakes, and soil loses all of its strength and pore water pressure increases. And then we have seen all over the world that this phenomena has occurred, and it has also caused a tremendous damage to infrastructures and other areas. One of the things is that in New Zealand in 2011 Christchurch and 2016 Kaikoura earthquakes have caused a tremendous amount of liquefaction and associated damage. So that was one of the key things which motivated us to do more research in this area in different parts of New Zealand, including the one which I'm going to talk today. So my study area is this lower Wairua Plain. So this plain is situated in the South Island of New Zealand, and this region is very famous for its lush green fields and also winemaking industry. So as you can see that the preliminary, the geotechnical forms of this map shows that there are sediments and loose soils present of sand, silt, and also gravelly soils which are intermixed with sand and silt. And also the groundwater model has shown that the groundwater depth is shallow, it's approximately 2 meters in most of the region. And other thing is that in 2016 Kaikoura earthquake, the liquefaction was also absorbed in some regions in this Marlborough district, for example, Blenheim. And then that's why we took up this project to do the mapping of the whole region and then do some of the site-specific analysis to see the sites where gravel is dominated, that how the soils will behave, and it can help in the future developments and future projects. So this figure shows some of the background. So before doing the numerical analysis, what I have done that first step was map the whole region, the GIS-based map. So there was a methodology adopted for that one, in which the idea was to just map using the groundwater depth, age of the deposits, and the sediment types to see which areas are prone to liquefaction, and liquefaction vulnerability is high, low, or medium. So as you can see in this figure, the yellowish part, this part, the liquefaction damage is possible, while in some of the other parts which are dark blue, they are the rocks and the liquefaction damage is not possible. And also some of the areas which we can say by certainty that low liquefaction vulnerability will be there. And also the hatched portion, the hatched cross section in this one, is showing that gravel-dominated soils are present, but still there is a possibility liquefaction will happen, and it has also happened in the previous earthquake in 2016. And the second step which I performed was getting the CPT data available in the New Zealand geotechnical data set. It is collected from all over the different projects. And also we performed some of the new tests which were dynamic probing tests, as the CPT is not possible in the gravelly soils, and those tests were performed, and also some of the analysis was done. And then it leads to the third part, which is the numerical simulation using effective stress analysis, and that I will explain in a bit more detail in this paper. This was a methodology adopted to perform the numerical simulations. So first of all, I selected the model, which is PM4 sand, as it's widely used for liquefaction analysis. And the program I'm using is Plexis 3D. Next step was validation of PM4 sand so that I can know that my model is working fine. For that one, I simulated a site in Christchurch where there was already results available so that I can compare that my model is working okay. And then I applied that model, my techniques, to the target sites in the lower Wairua plains. And then it leads to the main site characterization. So as I have already told you that there is a tremendous amount of data available in the New Zealand Geotechnical Database, and also some of the companies there, they are quite generous to offer their data, which they have done in different projects to use in the research in the university. So CPTs, boreholes, and all of these data was used so that we can see the soil characterizations. And then other laboratory test data, if something was available, we tried to collect that. And this analysis, I haven't performed any lab tests, but I've tried to gain some from the already existing ones. And then I simplified the site profile so that I can perform a 2D analysis in the Plexis software. It also lead to the calibration of the model and determining the parameters from the PM4 sand model. Next step was to obtain the earthquake input motions. For that, we used the GeoNet database, which is New Zealand based, and there were strong motion data set available from 2016 and other earthquakes which has happened in the region. After selecting those, I applied everything into the Plexis, and Plexis, there are certain steps which we follow. First of all, I defined the geometry, applying the material properties, input motions, and very important is the mesh generation and also thinking about the boundary conditions of the model, and then analysis. So this figure is showing the exact sites which were selected from the region. So you can see that the site A, and site B, they are more in the lower Wairua plain, close to the main town of Blenheim. These two sites are closer to the region where liquefaction was manifested in 2016, but not happened actually there. And then, as I explained already, after getting the data from borehole CPTs and whatever was available in the database, I simplified the profiles which I'm going to use for the analysis. So for site A, I divided it into two gravelly soils. This was mainly based on the relative density difference. As we go down, the relative density was increasing. So that was the differentiation point which was selected to have the gravel 1 and gravel 2. And it was 15 meter of depth for simulation. For the site B, it was a bit more, stratigraphy was a bit more changing, and then the silt and sand was also mixing into the gravel. And again, one of the main criteria was to see that the relative density is changing frequently from 3, 4, and 5, and then these depths were set to use in the Plexis. Next step was for the calibration. So for this one, unfortunately, we did not have any data available for the gravelly soils in New Zealand. There are some of the projects in pipeline in Canterbury University because they have the big apparatus in which the big mold can be used for the gravel because the specimen size is going to be bigger than the normal soil. But at that time when we were doing the test results were not available. So in order to do the calibration, I searched similar results from Hubler et al. 2018 for the gravel dominated soil, and relative density and the particle gravel size were quite similar. So that's why I used those ones. And you can see in this figure the liquefaction resistant curve from the PM4 sand model in the orange color, and from the laboratory cyclic direct simple shear tests in the blue color are quite similar. These are done by using the soil testing facility in the Plexis software and by curve fitting. So basically, after getting this curve fit, we can move on to the stress path and the stress strain behavior and see that if the other curves are also fine, so that we can use those parameters as an initial, and then we can also modify them using the equations from the developers of the models. So these are the other curves: stress strain, stress path, and the generation of pore pressure. These are shown for one of the tests, which is for CSR 0.09, and we can see that they are quite similar and in a good agreement to the lab tests. So it gives us a confidence to use it and for the calibration of the parameters. And it leads us to this slide, which is showing us the primary parameters of the model. So what is happening in PM4 sand model, that there are 3 primary parameters, and there is a range of secondary parameters. What makes this model a bit easier to use is that only 3 primary parameters need to be calibrated. We can calibrate the other parameters if needed, and in some of the other simulations I also did that for curve fitting, but in this specific one I used the default value for all the secondary parameters, and only the 3 primary parameters which are shown in this slide were calibrated. And you can see that this for site A, if you remember from this previous slide, that only gravel 1 and 2 were there, and these were the 3 parameters which are relative density, shear modulus coefficient, and HP naught, and similarly for the site B for sand 3, 4, and 5. One of the other things which I haven't put in the slide, but worth mentioning is that for the initial phase, not the dynamic phase, we use the hardening soil parameter. But then later on we use the PM4 sand model for the gravelly soils. And if there are silty, clay, or any other soil layers available, then we use the hardening soil model. And then the input motions, I used 2016 Kaikoura earthquake and 2015 San Arnaud earthquake records from GeoNet. And then you can see that the 5% spectral graph is also shown, and these 4 are used so that I can have a range of frequency content and have a more confidence in the results which I'm gonna get. So this slide shows or summarizes the overall response of site A. And this we can see that different responses are shown. For example, for the first one, the pore pressure ratio, we can see that the pore pressure ratio reaches up to 1 for the upper gravelly soils, and it tried to develop a bit in gravelly soil too also, but it did not reach up to a point where liquefaction can happen. So we can see that the first loose gravel soil will liquefy. And also we can see that the peak shear strain values are also fluctuating a lot, and they develop in this region, which is a liquefied layer. And maximum acceleration graph is also showing a variation in this region, mainly in this layer. And the post-liquefaction settlement, which were calculated using a 3rd phase in the Plexus software, which is the dynamic consolidation phase, to see that what happened when the dynamic loads are done, and then what is the settlement value. So this is approximately ranging between 30 to 35 centimeters. Similarly, for site B, we can see that the response is quite similar. The first one, which is a comparatively loose gravelly soil, this has pore pressure developing to 1. Similarly, peak shear strain developed in this one, and post-settlement liquefaction values are 20 to 30 centimeter. So it leads to the final slide of conclusion. So these are some of the conclusions from this paper. Site-specific numerical modeling showed that liquefaction would occur in site A and B, and this can also lead to a medium vulnerability of liquefaction. It also shows the importance of site-specific assessment in addition to CPT-based or just the geological or geomorphological-based analysis, because we can see the pore water pressure generation and stress strain behavior. Overall response is similar for site A and B, and also a use of range of input motion with different frequency content highlighted that in addition to PGA, other parameters like earthquake characteristics, soil properties may also influence the liquefaction response when conducting the numerical simulations. Thank you very much for listening.
Thank you, Dr. Omar. Any questions from the audience? The gravel you indicated in this study, how big the size it is? Is it ranging, is it fairly large or?
They are medium to large. I mean, there is a range of gravelly deposits available, and they are naturally deposited there. So, but yeah, they are like not too big.
So it's not that easy to collect the specimen and then do some testing in the lab.
Yes, so that's one of the challenges. That's why we were not able to do that. Right. But at the moment, they are in Canterbury University collecting some samples and doing that tests.
So from the literature, have you seen any other people using the PM4 sand model to mimic the behavior of gravelly soil like yours?
like Haber at all the paper which I have used, they have used PM4 sand model.
Right, but they're mainly for sand.
Yeah,
so
they
for
are-
the gravel
yeah.
type of
Yes.
soil, would that be applicable to the gravels from
Um,
your standpoint?
Yes, so I think that's a very good point because generally, even if they are gravel, the percentage of sand is the dominating one, and that's why PM4 sand model we are using. But at the moment, by preliminary research, I can say that it's also applicable, but maybe in future there's going to be a new model which can be like, now we have PM4 silt for more silty soils. So maybe for gravel or the bigger particles, there's going to be a new numerical model which can be used in future.
All right, thank you. Any other common questions? So let me ask one more question, since the audience is quite quiet. You mentioned that I think most of the site exploration program carried out in New Zealand using CPT, and then you also indicate that when you have a gravel formation, the CPT sometimes doesn't work. And you mentioned the term you have a special different way for the dynamic something.
Yes,
What's that about?
Yes, dynamic probing testing. So they use the dynamic ones so that the probe, it's like CPD but with a dynamic one, and then it can go into the gravelly soil. So that's called DPPH, it's like dynamic probing testing.
Is it similar to the CPT
Yes, the
setting?
results are similar. We still get the profiles, but it's dynamic, not just the static one.
Okay, okay, all right, thank you. All right, thank you, Dr. Omar. Thank you. Our next presenter is Dr. Dindaya Rahat, if I pronounced that correctly. He'll be presenting a three-dimensional finite element analysis of a offshore wind turbines monopiles under two-way cyclic loading. Thank you, please. Oh, I apologize that that presenter isn't here. So this is our staff here. It's not the presenter. Anyway, we're gonna have the last one. That will be given by Mr. Yufeng Lin from National Taiwan University of Science and Technology, sharing with us a liquefaction-induced settlements. So let me reintroduce our speaker. It's Mr. Yufeng Lin from National Taiwan University of Science and Technology. He will be showing us some study on the apparent viscosity on estimating the liquefaction-induced settlements. So thank you, Mr. Lin.
Yufeng Lin, I am delighted to be here with you today to share some results I gathered on the topic of the impact of viscosity on the estimate the liquefaction-induced sediment. So here is my outline. That will consist the introduction, methodology, discussion, and conclusion. And the author primarily come from two organizations, including the Taiwan Tech and a government organization in Taiwan, namely NCDR. And I am a PhD student and under the supervisor of the Professor Lu. So here is my introduction, and I will include in the background and the purpose. So the soil liquefaction has caused damage to the low-rise building worldwide over the past half century. For instance, in the 1964, the Niigata earthquake in Japan, it caused significant damage to many houses. And many countries has also suffered disaster impacts, such as the Turkey and Indonesia, Chile, and Taiwan also. So several research studies have shown a strong correlation between the building sentiment and the building geometric feature. So it's linked in this figure as the area of the building increase, the sentiment will also increase. So several research. So how do we estimate the building sentiment? So there are also some two kinds of the force, and I will be including the driving force and resistive force. So the method traditionally used in the past is the limit equilibrium method. So based on this kind of concept, our study attempt to introduce the viscosity and the damping force into our model. So we can determine the viscosity maybe through some dynamic experiments. And also we can get some parameter from the experiment and put this kind of parameter into our model and to derive the evolution of the building sentiment. So what is our goal? Our ultimate goal is to predict the final sentiment magnitude. So why this is so important? Because this kind of information is very crucial to the engineering design and the disaster assessment. And here is my methodology that will be consist the governance equation, and I will show you how to derive this kind of analytical solution. Sorry. So the model consists of three main force components that were including the weight and buoyancy and the damping force. So the building sentiment model is formulated by including these three forces in the formula of the Newton's second law, and it given as the follow, like this. And there are several assumptions we need to follow. So first one will be the groundwater is located at the ground surface. And also the ground motion are sufficiently large, so the liquefied soil will behave like the liquid. So finally, the submerged portion of the building during the sentiment will be surrounded by the liquid. Then we can solve this differential equation by using the mathematical technique. So we can see this equation will show like this, and our viscosity will present the like exponential decay law function, look like this. And we will follow this kind of boundary condition. So the result equation of the motion is as follows, look like this. So as you can see, when the time is long enough, the value, this value will tend to be approached to zero. So then we can get the stability condition that will look like this. And this one will be our discussion that will consist of the three parts. We can obtain the viscosity from several pieces of literature. So the value of the viscosity will fall within like this range, look like this. So also we can explication the viscosity within the time frame, 20 to 13 seconds. Yeah, that will be in this kind of the range. So why do we choose this direction? Because we can refer to the direction of the seismic event or some experiments direction. So in our study, we can use this kind of formulas and to do some investigation. So the viscosity will fall within the range of the 10 to 10 to the power of 3 kappa times S. So this sensitive investigation shows agreement when we use our model. So in order to show the evolution of the building sentiment, we assume the geometric characteristic of the foundation is 10 times 20 meters with a contact pressure 50 kilopascal, like this. So we can refer to the diagram on the right-hand side. In the blue line, we use the exponential decay law function proposed in this study to describe the transition of the soil matrix to the fluid state during the soil liquefaction, look like this. They will be decayed. So when we focus on the sentiment, then we will compare two kinds of analytical equation. One is proposed by Sawatsky in 2009. This formula look like this, and they will be presented in the orange line. And in our research, we use our equation that we present in the blue line, like this. So by using the analytical model, it's easy to find the final settlement in this scenario and share with the same final settlement. It's like this. So it indicates that the sentiment is correlated with the contact pressure under such assumption. And here is some further discussion. What if we introduce some other concepts, such as the soil color, to correct and modify the previously mentioned equation? So this is the previous mentioned equation, and we involve some concept, and maybe we can modify our equation. So in this concept has some potential to establish the link between the sentiment and the area of the building. So in this diagram, we draw the line represent the different building weights using this equation. So we can see there have several lines like this that will represent the different weight of the building. And additionally, we collect the historic case to compare them. So we can see there are 5 cases present here. So the results show that it provides some agreement to based on this kind of study framework. So here is my conclusion. So this study presents the statistical model for estimate the magnitude of the building sentiment. And the result, our study emphasized this is very important to consider the time-dependent viscosity in liquefied soil. And there are 3 topics for oncoming study. First, we need to establish the suitable model to involve into our model to describe the time-dependent viscosity through the dynamical experiment. And secondly, we also need to take in the non-liquefied crust into consideration. Somehow the reduction factor should be included in our model. And finally, it is important that we construct a general model, and then maybe in the future, then pursue some further study on the dynamic response during the building sentiment. And thanks for your attention. I really enjoy being here. Thank you.
All right, any questions? Yes, please.
Thank you for a nice presentation. I just imagine that the viscosity may change due to the particle soil properties like particle size distribution or something else.
Yes.
So how did you consider, how will you consider about it?
Okay. So as we know, the viscosity is maybe will be the function. Maybe the function of some RU or DR isolation or uncycling. So right now we just do some first study on this kind of parameter. So maybe in the future we can combine some dynamical experiment and can get some parameter info into our viscosity function.
Okay, thank you very much.
Thank you.
Any other questions? Or in the back over there, please.
I noticed that your building is like symmetrical. In case of the irregular shape of the building, does this equation still valid to determine the settlement or not?
Because right now, in my assumption, our building is like the base of the foundation is rectangle. So maybe we can do some geometrical transfer and maybe transfer to another shape. So maybe in the future, we will also do some further study on this based on this kind of study. Thank you.
Yes, also the one in the back.
Can you tell us the effect of the weight of the building to the result of settlement?
You mean the direction?
The weight of the building.
The weight, okay, the weight of the building. Okay. Oops. So from my statistical model, the formula shows when the building is heavy, the sentiment will be increased. So maybe this equation is too simple. So maybe we can infer another concept, such as some additional force to work to up and resist the building to make the building to not too much sentiment. So, like I said, when the building is more heavy, the sentiment will be increased. Thank you.
I think the key is the apparent viscosity that could be depending upon quite many factors that you indicated earlier. So how to quantify them into determine this viscosity, I think is the most
because
important.
Because viscosity doesn't affect the final sentiment. It only affects the evolution of the sentiment. So right now, maybe in the future, we can do the further study and combine these two kind of concepts together. And we can do some further study on this topic.
Mm-hmm. Any further questions? So if not, thank you, Mr. Lin. Thank you.
Thank you.
Let me check again if our presenter...
King Jason O, Mahabab Sadiq, and Chia Shun Chai. Sorry that I couldn't say that you are a professor, doctor, Mr. Mrs. Just a name. Sorry about that. And Cheng Yao He. Okay, so these 4 persons. Please go to the payment counter to get your receipt. Yong Pin Jason O, Mahabab Sadiq, Chia Chun Sai, and Cheng Yao He.